guys, Mr. Backerwork here. In this video, we're going to look at exponential growth and decay models. So in this first example, we're going to look at modeling some bacterial growth. We've got a culture containing 100 bacteria, and we're going to put that into a petri dish. Now, as we're tracking the population, we see that the culture doubles in population every hour. So we want to figure out when the number of bacteria is going to reach 350,000. So if we start to think about a population model, that's P of T equals our initial population times 1 plus the rate of increase or decay raised to the T power for time. Now, as we think about what we have happening in this example, we've got an initial population of 100 bacteria. Now, talking about that population doubling, that actually means that we're increasing at a rate of 100% per hour. So after the first hour, our population would go from 100 to 200. So with that R value of 100%, inside of my parentheses, if I fill in that R value, I'm going to turn it into a decimal, and that's just going to be 1 raised to the T power. So we've really got 100 times 2 raised to the T power. Now, in this example, our time, we're talking about hours, so my T value really represents hours. Now, if I'm going to try to figure out where my population reaches 350,000, I'm going to use my calculator to help me out. So in my calculator, I've got two equations typed in. I've got my population model, 100 times 2 to the x power, but I'm trying to figure out where this population is going to reach 350,000. So I have that typed in as my second equation. Now I am going to need to adjust my window, so I'm going to hit my window button. I'm going to extend my x max out to 20, and my y max, well, I'm trying to figure out where my population is going to reach 350,000. So I need to go above that, so I'm going to make my y max 400,000. Now when I hit graph, we'll get a picture that looks something like this, and we're trying to figure out where our lines are going to intersect. So I'm going to go second, trace, and I'm going to pick option number 5, intersect. I'm on my blue curve, so I hit enter. I'm on my red curve, so I hit enter, enter. So that tells me at an x value of about 11.77, our y value population will reach 350,000. So we got an x value, or a t value, of 11.77. If we think about what that means in the context of this problem, the 11 means 11 hours, but the 0.77 does not mean 77 minutes. Remember, there are 60 minutes in an hour, so if we think about that 0.77, if we think about that percentage of 60 minutes, then that's really about 46 minutes. So after 11 hours and 46 minutes, our population will reach 350,000 bacteria. In our second example here, we're going to look at modeling radioactive decay. So suppose the half-life of a certain radioactive substance is 20 days. We want to find the time that it's going to take for a 5-gram sample to decay down to 1 gram. So we can sort of think about this as using our population model, but since we're not really talking about a population, I'm just going to call this function f of t. We're still going to be looking at our initial sample at the beginning, so that's going to be our 5 grams that we've got. Now, inside of my parentheses, when I take 1 plus that r value, we have to think about what the half-life means. The half-life means that we're losing 50% of what we started with. And because this is going down, we can think about that like a negative 50%. So if I think about that negative 50% as a decimal, it's negative 0.5. And if I add negative 0.5, then I've really got 5 times 0.5. Now, the time is going to be a little tricky to think about. We know that our half-life is 20 days, but if we wanted to look at a certain percentage or a certain fraction of those days, what we're really going to do is take t over 20. So my function is going to be f of t equals 5 times 0.5 raised to the t over 20 power. Now we're going to try to figure out how long this takes to decay to 1 gram, so I'm going to use my calculator to help me out. So in my calculator, I've got my two equations typed in, my 5 times 0.5 to the x over 20, and my 1. I will have to adjust my window, so I'm going to hit the window button. I need to extend my x max out to 50. Now when I hit graph, We end up getting this picture. I want to find my intersection, so I'm going to go second trace and pick option number 5, intersect. I'm on my blue curve, so I hit enter. I switched over to my red curve, so I hit enter, enter, and that tells me at an X value of about 46.44, we'll be at a 1 gram sample. So with that T value of 46.44, our T represents our days. So this is going to be 46 days. And if we want to take that 0.44 and convert it into hours, well, there's 24 hours in a day. So if we take 0.44 times 24, we get about 11 hours. So after 46 days and 11 hours, this 5 gram sample will have decayed to a 1 gram sample. In this example, we're going to look at determining altitude from atmospheric pressure. So scientists have determined that the atmospheric pressure at sea level is about 14.7 pounds per square inch, and the pressure gets reduced by half for every 3.6 miles above sea level up to about 50 miles. We want to find the altitude above sea level where the pressure ends up being 4 pounds per square inch. Now we're going to think about this sort of like our population model, but we're going to be thinking about pressure based on our height. Now our initial pressure at sea level is the 14.7, and the pressure is reduced by half, meaning that we're losing 50%. So inside of my parentheses, I'm going to be taking 1 plus a negative 0.5. And as far as that height, we're looking at the height compared to that 3.6. So I'm going to be taking h over 3.6. So if I look at simplifying this down a little bit, it's going to be 14.7 times 0.5 to the h over 3.6. And we're going to figure out at what altitude the pressure is 4 pounds per square inch. So I'm going to use my calculator to help me out. So in my calculator, I've got my 14.7 times 0.5 raised to the x over 3.6, and I've got my 4, since we're trying to figure out where the pressure is 4 pounds per square inch. When I hit graph, we'll get a picture that looks something like this. We want to find the intersection, so I'm going to go second trace and pick option number 5. I'm on my blue curve, so I hit enter. I switch over to my red curve, so I hit enter, enter, and we get an x value of about 6.76. Meaning that our height is about 6.76 miles. So the atmospheric pressure is 4 pounds per square inch at an altitude of 6.76 miles above sea level. That's going to be it for this video. Thanks for watching.